So the reason for telling the story is that Paul and I have a different view of what the solution to the problem was. So you see this 55-gallon drum, and you see, M&Ms as far as you can tell from the top. And the question is the drum full or not? And so Paul is an experimentalist. He says the way you do it is you take your hand and you go like that and see how far down your hand goes. I tweaked it like that, and I heard the thing ring. So I knew it wasn't full, but he said that wasn't a good solution. The other thing is that we got cheated with our book because there is a clause in our book that says that we have rights to television shows and things like that. And Cambridge never, ever admitted that they gave the book to this thing. But we've gotten enough mileage out of it to... okay, now let me see. Do I have everything I need here? I don't know. Wait till it goes on. So I've been charged, to discuss soft physics at Penn. It's a really big subject. As you can tell this morning, I would say, half the talks had some component of soft. But Penn is in a unique position that we were one of the first places to really capitalize on soft as a legitimate materials program, interdisciplinary materials program, and it's responsible for our having a worldwide reputation now for being one of the centers of soft matter. So I will tell you, as I say, I can't tell the whole story because there's too much of it. So what I thought I would do is just tell some, parts of the story. So, again, the standard congratulations, etc. So really, this soft matter... What's so funny? Okay. So it really is one of the success stories. And I don't know, are NSF people in the audience? None. Oh, see. Well, I was going to, butter them up a little bit. I would say it's one of the real success stories of the NSF itself. Basically, the MERSEC forces people who might want to sit in their rooms like me and, fiddle around with epsilon expansions and say, look, you have to talk to real people. And so on several occasions, the force of having to write a proposal for the MERSEC caused me to change directions and then have the pleasure of working with experimentalists. So, the things that have been done at Penn that are soft include colloids, liquid crystals, emulsions, lipid bilayers, biopolymers, etc. More and more of them. Now, one of the things that what was really necessary to have a good soft program was that you needed people to make things, you needed people to characterize, you needed all the things that are part of the front piece of any MERSEC proposal. You want to put all of these things together, and in fact, it was pretty rare when we started off having a chemist who would talk to a physicist and actually make things. For example, in the liquid crystal world, most of the molecules are not complicated enough to really engage a serious chemist, and to find a chemist who would make things was hard. So in the early days, we had Ken Swager, who was willing to make nice columnar or discotic liquid crystals. We now have Virgil Perchek, who makes things that are fairly exotic, and they play an important role in the whole soft matter story. There was a lot of X-ray work here, modeling by Klein, etc. So what I'm going to do is to tell you a little bit of some interactions I've had and how they developed over time. So one of the things we looked at early on were liquid crystals. I, of course, had done a lot of work on liquid crystals starting back with my postdoc. I'll remind you what they are. Pneumatics are these aligned rods, and they have interesting topological defects, which include a disclination, the two things at the top, and hedgehogs, which are basically the director points everywhere radially outward. So when Dave Waits arrived, he was one of the world's experts on colloids and emulsions and packing of them, and I knew about liquid crystals, and we had to write a proposal. So we got together in a room and said, okay, what can we do that will draw upon both of our expertise? So we came up with the idea of doing liquid crystal emulsions, which is to mix together water, surfactant, and a liquid crystal and see what happens. Now there are thousands of papers that have been written on this subject. It's almost an everyday occurrence, but at the time, nobody knew how to put a liquid crystal in water and keep it there. So this guy, we hired a postdoc, Philippe Poulin, from Bordeaux, and he was one of these magicians with things. He could get anything to happen. And we did manage to mix together. So you can see there are two different versions you might have. you can have the water on the outside and the liquid crystal on the inside. The liquid crystal molecules typically have a hydrocarbon tail on them, so they don't like water. And you put a surfactant in, and the surfactant will immediately shield the liquid crystal from contact with water. So you can see if you have the one on the left, things are pretty simple. Well, simple in the sense that you have the closed container for the liquid crystal, and it'll form whatever topological defect the boundary conditions require. But if you have the other form where you have water droplets in a liquid crystal background, then if you have tangential boundary conditions at the bottom, you get something like this, but it has to connect with the other ones, or the radial boundary conditions, things stick radially outward, and you don't know where the things are going to go. So the result was, we made this, these are multiple emulsions. Gee, maybe I'll use this. So here we have, this is under cross polarizers where it's black, it's isotropic. This is the liquid crystal. This is the surfactant. And then we have water droplets on the inside. Now notice the water droplets are chaining, and each water droplet will create around it what's called a hedgehog, where the director, the anisotropy direction, points radially outward. So here's one where we have a single water droplet in the middle of a pneumatic droplet. And so the droplet in the middle forces radial arrangement at the center, and the surfactant on the outside forces radial arrangement at the end, and so we get this perfect cross under cross polarizers with 90 degrees to each other. Now, if you look at this line, which we blow up here, you can see between each of the water droplets, there's a little defect. And that's needed because the total charge, the total topological charge on the outside is 1, because that's what the boundary conditions say. Each sphere nucleates a local hedgehog with charge 1. And so if I have one water droplet, I'm okay. But if I have 2 water droplets, I have too many hedgehogs in the middle, and I have to draw up something from the inside. And what happens is you get a configuration that looks something like that. And this actually spawned a field. I would say that almost 50% of what's done in liquid crystals now, in one way or the other, deals with this. And just to show you the neat things that spawned, you can, instead of having this point defect that cancels that, you can have a ring, or you can have a Saturn ring and close it. And there's some really neat work that's going on in Slovenia now, where you can take colloidal particles and wrap them with the disclination lines, and you can tie knots with them and form random things and so forth. And you can control how they work with lasers, where you come in and you break the disclination and put them back together again. So there's some stuff. So amongst other things that I worked on was something called pneumatic elastomers, which are basically pneumatic liquid crystals that are rubbers. And so the idea occurred to us that maybe it would be nice to make a lytropic version. And I remembered some old papers by Toya Tanaka about NIPA gels, which undergo a first-order phase transition in volume as a function of the temperature or the concentration of the salts. And so I thought it would be a good idea to put carbon nanotubes, which Mohammed Islam had figured out how to disperse, in a hydrogel or NIPA gel and contract it to see if we could produce a pneumatic. And, you know, we did in sorts. Here, this shows a picture of the ribbon, and you can see that at the edges it looks. So there was a success there. But the interesting thing is to see how science develops. Arjun learned how to use NIPA, and then he had all kinds of neat ideas about what to do with it. Whoops. Well, isn't that something? Oh, no, there it is. Okay. So, you know, you can make spheres of this NIPA, and by changing the temperature, you can change their volume. So now you have a method of changing volume fraction of colloids without making different samples. You just change the temperature and you change the volume fraction. So there are all kinds of neat things you can do. Here's one thing that Arjun did, which shows, you know, the breadth of things. This is a pre-melting of a grain boundary, which you can see, you know, that the thing wants to be a crystal if you make the volume fraction large enough. If you have a grain boundary and you're not quite ordered, then what happens is the fluctuations get larger near the grain boundary. And this is the sort of thing which would be very hard to see, you know, directly in a metallurgical version of this crystal. Another thing we did was to take a two-dimensional cell whose diameter is whose height is slightly larger than the diameter, and if you put the particles want to go into a nice hexagonal lattice, but to give them the best packing configurations, they want to go one up and one down. If you have one up and one down on a triangular lattice, you've got an antiferromagnetic Ising model, and we were able to study this and then learn the difference between this and a real antiferromagnetic Ising model, because if you raise one layer and lower the other one, then you actually change the distance along this direction instead of that direction, and we then were able to show that the actual compressible three-dimensional Ising model, rather than having a ground state entropy that is proportional to the number of particles, it's proportional to the square root of the number of particles. So here's just another totally different thing. Waits and Mason had invented this method of measuring rheological properties of actually any material by looking at little beads embedded in it. So if you look at a little bead and you watch its fluctuations, by the Einstein relation, the fluctuations are related to the viscosity of the system. So in principle, you can measure the viscosity or the frequency-dependent viscosity by just looking at the fluctuations of the bead. Alternatively, you can come in with a laser tweezer and drag the bead and measure what the response is and get the results. So John Crocker, who's in the audience, I presume. You here, John? No, he's not here. Okay. Anyhow, he had done a lot of the original experiments after the original ones, and he noticed that there was a problem with the one-particle microreology because the bead itself will distort the medium. So it's a little bit like I found it easiest to think of a metal sphere in a dielectric medium where you allow the sphere to distort and change the dielectric constant in its vicinity. So if you measure the capacitance of this guy to ground, you cannot measure directly, unless you know what's going on in this sheath, the dielectric constant of the medium. If there were no sheath, measuring the capacitance would give you the dielectric constant of the medium. But if you measure the mutual capacitance of these two things, and look at the coefficient of 1 over r, you can actually measure the capacitance, the mutual capacitance. And the same thing happens with displacements. So if you measure the correlation of the displacement of 1 relative to 2, you get a much better measure of the dielectric constant. And so Alex Levine and I worked out the theory for that, and it seems to work fairly well. Oops. The sort of things we looked at it with is you can look at, for example, living matter. You can look at little the polymers inside a living cell, track them in the same way that you can track the beads, and you can then determine whether or not the fluctuation dissipation theorem is obeyed, whether you have, the fluctuation will be different from what happens if you drag. And indeed, it turns out to be different. This is what, so we have a frequency-dependent viscosity, which would give a noise that looks like this if it were thermal, and we measured something that was several orders of magnitude larger, and that's to be expected. Within a living cell, you're going to get kicks that are not just thermal. They come from the little motors running around and so forth. And we also applied the same idea to bacterial baths. So there's been a lot of work on things like flocking of birds recently, active matter, in which you have little motors or objects that move around on their own accord and provide their own source of noise. And so we put, Dan Chen and Arjun's crew put the beads inside of a bacterial bath, and we found that there was superdiffusion. A particle would go more, delta r squared went as r to the 3/2 instead of t, as t to the 3/2 rather. If it were diffusion alone, it would be delta r squared as t, but it moves faster, indicating that you have an exotic correlated motion of the bacteria that give rise to. And this is a field, various versions of this active media are one of the big fields now. So to close, since I was only supposed to do 10 minutes, if you look at each of the 4 IRGs we have now, in every one of them you can find something that has to do with soft physics. I mean, the last one is a little, is not quite so strong, but looking at how nanoparticles of various shapes self-assemble is one of the canons of soft physics. So I think we can say that it was nice to have soft physics on board, and it's still vibrant here.